Hey everybody, welcome back to For You Physics YouTube lessons. Continuing on with our circular uniform motion unit, I just wanted to add on a little bit about planets, orbits, satellites, and things. So we'll talk about that today. The first topic I want to talk about is gravitational fields. Okay. What is a gravitational field? A gravitational field is a region of space surrounding a body, anything with mass. Gravity and mass are interlinked with one another, in which another body experiences a force. And that force is of gravitational acceleration, or gravitational attraction, shall I say. Gravitational attraction. There we go. So, I mean, we're all kind of intimately familiar with gravity, right? And let's say this is some huge mass like the Earth. What this is saying is that anywhere around this blob of mass, there is always some sort of field. And any mass that enters this field will experience a force towards the center of that blob of mass. So the Earth is a really big mass, so it gives off a huge force, and any little thing on the Earth that is within that field will feel a force towards the center of the Earth. It's what's holding everything on the Earth, right? And we all know the acceleration that that force gives us. It's 9.8 meters per second. By definition, this field strength is given the letter G. Okay, write what that means in a second, and it's equal to big G times m divided by r squared. So what's little g? Little g is the field strength. Okay, what units are it in? Is it in? Well, it's in newtons per kilogram. Another fancy way to say newtons per kilogram is meters per second squared. Those are the same things. Okay? Try to see if you can figure out why those are the same things. And so for the Earth, it's 9.8. We'll figure out how we come to that number in a second. M is the mass of the object, obviously. That's giving off the field. I mean, everything with mass gives off a field, right? People give off gravitational fields. You know, bugs give off gravitational fields. Anything with a mass gives off a gravitational field. You just don't normally feel it because it's so small. You actually have to have a really huge mass to actually be able to impart some sort of acceleration onto something. That's why usually we only look at it when it comes to planets. And r then is the distance from the center. Distance from center. Running out of space here. Okay. So that's good. Let's look at the gravitational field strength of the Earth at the surface of the Earth. So if I write the gravitational field strength of Earth, it's this big G, which I haven't written yet, times the mass of the Earth times the radius of the Earth as well, because when you're at the surface, you are at a distance of the radius of the Earth, and that is squared. Big G is just a constant. It is equal to, it's constant 39 on those Casio calculators. It's a very tiny number, which is also why small bodies don't exhibit or give off a lot of force. And the units for that are, I don't really feel like working it out right now, but it's like kilogram meters per second, something. Don't worry about the units for now. You could figure it out from this equation anyways if you need to right here. All right, so what's the mass of the Earth? Does anyone know? I do. It's equal to 5.98 times 10 to the 24 kilograms. That's a very big number. It is basically the number 6 here with 24 zeros after it. The radius of the Earth is equal to, I can't even remember. Look it up. Earth radius, does it say? Yep. 6,371 kilometers. So, if I want to write that down, there's a little pen here. 6 point, do I want that point there? No. Erase here. A little better with this thing. Is that going to erase anything? There we go. Perfect. 6,371, that's kilometers. So I obviously need it in meters. Basically 6.4 million meters. It's actually not that big if you think about it. 6,300 kilometers is not a huge distance to cover. So if it were easy to get to the center of the Earth, we would have got there by now. All right, so let's plug these numbers in and find out what the gravitational field strength of the Earth is. And so I'm going to plug in my calculator, constant 39, or just this big G value here. I'm going to times that by 5.98, the exponent 24. And then I'm going to divide that by my radius squared, 6371000 squared. And lo and behold, I get this number, 9.8 meters per second squared. So, I mean, you've been seeing that number in grade 11 a ton, and in grade 12, and that's where it comes from. It comes from the mass of the Earth and the radius of the Earth. Cool. All right, so anything that is at a distance of the radius of the Earth, so basically anything on the surface, will experience a acceleration from the Earth just because of gravity, because of its mass. And by the way, if you have a small mass, then you also exert a force on the Earth, because Newton's law says every force has an equal and opposite counterforce, right? So you're actually giving force to the Earth all the time, but the Earth is, again, 6 with 24 zeros in mass afterwards. So and you have almost no mass, so you're giving the Earth some tiny little force, and it's not affecting it in any way. But the moon has a big mass, and it's able to pull on the Earth and, you know, cause tides and cause all kinds of stuff, right? Where's the moon? Does it say? Luna. It's got a decently sized mass. It is, you know, here it says 73 times 10 to the 21, and the Earth is 5,000, 6,000. So, I mean, that's pretty, you know, the Earth is significantly heavier than the moon. However, the moon can still pull on the Earth and give it some noticeable force. All right, so here's a cool question then. We've been talking about things going around circles, uniform circular motion, right? So if this is my Earth, and I want to go around the Earth in orbit, let's say, and I want to go at a uniform speed. I don't want to be picking up speed or slowing down, obviously. Let's look at some of the math of that, because the force that's going to pull this thing or keep this thing from going around in a circle is just going to be the gravitational, the field strength from the Earth. So if we're going to look at a question like this, what we could say is if gm over r squared, now that's our that is our field strength, right? If that's going to equal the centripetal acceleration of something, that's going to move around the Earth at a constant velocity. What's going to happen if we kind of work out some variables here, right? And say, well, a centripetal acceleration has been defined for us as v squared over r. Let's say I want to solve this equation for velocity. I'm going to bring this r up, and so that one will cancel, and I'll just be left with g times the mass over r, all square rooted. So I know the mass of the Earth, right? And I know the radius will be kind of like the height up. The radius will be the radius of the Earth plus the height of however high up I want to go to get around, to go around the Earth. So let's do an example question with that. Okay, so here's my orbital speed, I guess we'll say, orbit speed. And it's going to equal the square root of g. That's a g, not a 6. Times mass of the Earth divided by the radius. Here's an example question. Example. What speed must the, this stands for International Space Station, by the way, travel at in, oopsie, let me get my eraser. Just really brutal with this tablet thing. Getting better. In order to orbit 350 kilometers above Earth. And that's about the right number. I think that changes a little bit depending on where it is in the orbit, but also find the period as well. So meaning how long does it take for this thing to circle the Earth once, okay? So it is only about 350 kilometers above the Earth, not too high up there. And we'll do a question where we'll figure out if there is gravity up there, and look at why the heck these people, maybe we'll do that after this question here, why the heck astronauts are floating in there then, if there should be gravity up there. So we'll do that next after this. Let's get our numbers first. Obviously the mass of the Earth we need, I think most textbooks say 5.98, but I think that has changed to like 5.97. I'm going to just keep it at 5.98. It doesn't matter if we're off in the by a digit there. G is equal to 6.67 times 10 to the minus 11. Still haven't figured out the units of that, but hopefully you guys can do that. It's not hard to do. And then the radius is going to be the radius of the Earth, which we already said was this big number, 6.4 million meters, plus an extra 350 kilometers, right? So that's actually going to make a difference to our new radius because we're now above the surface. And so when I punch that number in the calculator, I am going to get 672. And I should write this in scientific notation, but I don't feel like it. Meters, okay? All right, so let's figure out what our velocity then is. We're just going to plug it up into this equation here. Does this thing actually highlight? Man, that's nice. We're just going to plug it into that equation there. All of our numbers. So I'm just going to do that on my calculator here. Obviously, I'm going to write G times the mass of the Earth, 5.98 to the exponent 24. I'm going to divide by my radius, 672.1, 1, 2, 3, hit equals, square root that number, and I get a really fast speed. I get, where's my pen? 7,000, approximately 7,700 meters per second. Or, if you think about it, it's 7.7, kilometers a second. That's really, really fast, right? This thing is definitely booting around the Earth really, really quickly. If we want to figure out the period, it's just going to equal 2 pi r over velocity. Remember, velocity equal 2 pi r over t. If we want that in seconds, I'm just going to go 2 times pi times my radius, which is this number here, 6721000, 6721123. It equals, divide that by my velocity, which is 7,700 meters per second. And my period is this number, 5484 seconds. Let's figure that out in hours, maybe. How many, or maybe in minutes. I'm going to divide this by 60, and I get 91 minutes. 91.4 minutes. So that's how fast this thing boots around the Earth. It completes a revolution around the Earth every 91 minutes. So you probably get pretty bored up there after a few hours of just flying past the Earth all the time. You'd be going through like day and night cycles constantly too. Every 45 minutes it gets completely dark. That would be weird. Probably throw you off a little bit. The other thing I talked about is that people are weightless up there, right? Why are people weightless up there? Let's look at a free body diagram. Boom. Okay, so here's, our buddy Chris Hatfield or whatever. He's in the spaceship, yes. And that's the spaceship. And what forces are on this guy? Well, he's got gravity on him. He does have gravity. He is right near the Earth. What is his gravitational force? His gravitational force is just this field strength, which is equal to this big G times the mass of the Earth times his radius away from the center of the Earth squared. Okay? Let's figure out what that is. Saying that R is 6,7, whatever it was from the last page. What was it? Let me see. 6,7, this one right here, 6721000. So let's say he's in that space station, right? So R is equal to 6721000 meters. So let's figure out his field strength, what acceleration is on him, what gravitational force is on him. Constant 39 is my G, times 5.98 to the exponent 24, divided by that radius squared, 6721000 squared. It equals, there is a force on him. It's a little bit smaller than 9.8. It's 8.83 meters per second squared. But that force is still there, right? And so that's the acceleration on him. And I also got to put his mass on here. So that's good. He's going around in a circle like this around the Earth. and the Earth is like way down here somewhere. Okay, so he's zipping around the Earth. He does have gravity on him, right? And that's one force. And so if we're looking at this from an outside perspective, let's add up all the forces on this guy and let it equal his mass times his acceleration. Okay, so there's only one force on him. It's m times 8.83, and that has to equal his mass times his acceleration, which is the centripetal acceleration. So the masses cancel. It doesn't matter how much you weigh up in space. Everyone still feels the same forces. But now we can essentially say that the centripetal acceleration has to equal the acceleration of the Earth. Okay, that pulls on him. So basically what we're saying then is, because he's in the spaceship, should he have a normal force like this? The answer is no. Okay, he has no normal force, and that's because the Earth's gravity has to equal his centripetal acceleration in order for him to go at this constant velocity and not fall back down to Earth. Okay, if he does have a normal force, then he's either A, falling back down to Earth, which is no good if you're in a spaceship, or B, flying out of orbit of Earth, which is also no good. So here, if we say 8.83 equals ACP, you have to say he has no normal force, so he is going to be floating in space. And then you can solve for the velocity and depending on what radius you want to be above the Earth, right? So 8.83 has to equal v squared over r, and you can pick your velocity and your radius, and you will maintain a distance around the Earth that, let's say, in the terms of the space station, that they always want to be 350 kilometers above the Earth, right? So it's 350 plus 6,371 kilometers. Then they will figure out the speed that you have to go to maintain that altitude, assuming that you have no normal force. And that's how the spaceship works. You always end up at the same distance above the Earth at all times. You give yourself enough rocket fuel to get to the speed you need. We figured out that that speed was 7,700 meters per second, right? And you will just float around in space in the same orbit. The only problem is with the astronauts, they don't get to feel any gravity up there, so it gets annoying probably, right? We discussed that you could rotate a spaceship, but we can't really make space stations that big yet and that circular and get them up there. The International Space Station is just a bunch of these little pods. And the other problem is if you're spinning it, you can't have any windows in there, or else people will look out and get sick. So that is gravitation. And maybe I'll get you to try some questions from the textbook. Let's just look quickly here. I think it's chapter 6 in the book. Yes, it's just a little add-on to chapter 6. So I will find a few interesting questions here. Maybe try these two practice questions. They're on page... Let's look. And they also have some gravitational field strengths of other planets. If you can see that Saturn, though, even though it's way heavier than Earth, it has like a very similar gravitational field strength. Jupiter's the only one that's way out there. Mars is actually really low too, 3.7. So if you went out to Mars, you would feel super light, like 60% lighter than you do. Venus has a pretty close to Earth. Mercury's really light, but all of them are around 10. So yes, try these two practice questions here. And if you're interested, you can see this equation, which we didn't really look at too much. It's force equals gmm over r squared. That's basically just F equals ma. Ra is just gm over r squared, and then the other force is m2. So some of these questions, I don't want to dig too deep. Obviously, we're just working from home and stuff. So just try those practice questions, and if you're interested, have a look at some of these too. Okay, and we'll talk soon. I have one more section I want to talk about, and then we'll try our little quiz. I'm going to put your marks into Markbook or into Google Classroom so you can see them. And just obviously, it's probably your mark is just going to be really, really close to the best mark you got on the first two tests. So drop the worst one, but there's quizzes in there that'll affect it a little bit as well. And so those will get sent away to midterm. So everyone will have a really strong mark in the class, which I'm okay with because you've had your whole semester trashed anyways. So I don't see a problem in everyone. It seemed like everyone, for the most part, knew what was going on really well. So if you end up with like class average of 95, whatever, do not care. Just want you guys to learn some of this stuff so that you're not completely lost when we come back, or if we don't get back, then first year university, you'll definitely have some good background to work from. So that's the goal here. Post those marks in Google Classroom. You probably already know your mark anyways, but we'll do that. And so don't sweat that. And I think April 23rd is when those midterm marks are due, so you'll all have a pretty good midterm mark in my class anyways. So stay tuned for more. Talk to you soon.